This session is about the particle model of matter, which is in paper 1 and is in both combined and triple science. First of all, density. If you look at the diagram on the top right, the two objects are the same volume, but the object on the left has less particles in that volume compared to the object on the right. This means it's a lower density. Density is equal to mass divided by volume. Density is measured in kilograms per meter cubed, mass is measured in kilograms, and volume is measured in meters cubed. We did a required practical on measuring the density. To measure the mass, you use an electric balance. To measure the volume of the object, it depends on whether it's a regular shape or an irregular shape. For a regular shape, the volume is usually the length times the width times the height for a box shape. For an irregular shape, there are two methods you can use. You can use a measuring cylinder or a displacement can. Look at the diagram on the top right. This is how you measure the volume using a measuring cylinder. If you have a volume of water already in the measuring cylinder and put your object in, the volume of liquid will increase by the volume of the object. So by taking the two values away from each other, you can find the volume of the rock. Can you work out what it would be from this diagram? The higher value is 46 and the lower value is 18. So the volume of the rock must be 28 centimeters cubed. For a displacement can, you fill the water up to the bottom of the spout so that it's right on the edge, just about to pour out. Then you carefully lower your object in, collecting any liquid that comes out in a measuring cylinder. The volume of liquid displaced is equal to the volume of the rock. In this case, it's 14 centimeters cubed. The particle model can be used to explain the difference between solids, liquids and gases. For a solid, the particles are close together, they're fixed in position, they're vibrating around that position, they have strong forces holding them in place, which gives them a very high density and a fixed volume and fixed shape. Liquids, the particles are still very close together, but they can now flow past each other. They're no longer fixed in position. This means there are weaker forces between the particles, but they still have a high density. They have a fixed volume, but they take the shape of their container. In gases, the particles are widely spaced. They move with random speeds in random directions. This is called Brownian motion. There are very weak forces between the particles, and it has a very low density. It takes the volume of the container and the shape of the container. The change of state is a physical change, which means it can be reversed, and the mass of the material remains constant. The ones you need to know are melting, going from a solid to a liquid, freezing, going from a liquid to a solid, boiling from a liquid to a gas at the boiling point, evaporating, which is going from a liquid to a gas but below the boiling point, condensing, going from a gas to a liquid, and sublimate, going either from a solid to a gas or from a gas to a solid. The internal energy of a material is made up of the kinetic energy and the potential energy of its particles. Internal energy is the energy stored inside a system by the particles, the atoms or molecules that make up that system. If the temperature increases, the kinetic energy increases, the particles start to move faster, and this means the internal energy also increases. If the material changes from solid to liquid, the potential energy of the particles increases, so the internal energy also increases. And the same happens when you go from a liquid to a gas. Specific heat capacity is the energy needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. When the temperature of the object increases, it gains thermal energy, and when it decreases, it loses thermal energy. And we can work this out using mass times specific heat capacity times the change in temperature. E equals mc delta theta. M is the mass, measured in kilograms. C is the specific heat capacity, measured in joules per kilogram degree Celsius. And delta theta is the change in temperature, measured in degrees Celsius. The definition of specific heat capacity is very important and you need to learn it, but the equation is on the sheet given to you in the exam. When a material changes state, we talk about the latent heat. It's the amount of energy required to change the state of 1 kilogram of a substance without changing its temperature. And energy is equal to the latent heat times the mass. The energy is measured in joules, the latent heat in joules per kilogram, and the mass in kilograms. We talk about the latent heat of fusion, and this is when the material changes from a solid to a liquid. We also talk about latent heat of vaporization, and this is when the material changes from a liquid to a gas. We use the same equation the whole way through. It's just a slight change in the definition. So, for example, the latent heat of fusion is the energy needed to change 1 kilogram of a material from a solid to a liquid without changing its temperature. Whereas latent heat of vaporization is the energy needed to change 1 kilogram of a material from a liquid to a gas without changing its temperature. If you're changing from a solid to a liquid, heat is taken in. But if you're changing from a liquid to a solid, heat is given out. A similar thing happens going from a liquid to a gas. Heat is taken in, and from a gas to a liquid, heat is given out. You also need to be familiar with this graph. This is a graph of the heating ice practical that we did. The ice is taken out of the freezer at about minus 20 degrees Celsius. And we start to heat it over a Bunsen burner. At this point, the particles start getting faster and the temperature rises. But then it gets to a point at 0 degrees Celsius where we're still heating it, we're still putting energy in, but the temperature is not increasing. This is because the ice is melting and it's using the energy from the Bunsen burner to break bonds between the particles to change it to a liquid. It's only once all of these bonds are broken that the temperature starts to rise again and it's fully liquid. This continues with the particles moving faster and faster until it gets to 100 degrees Celsius. And here the liquid is boiling and the energy is again being used to break bonds. In a gas, the particles are in random motion, called Brownian motion. They move in random directions with random speeds and collide. Gas pressure is caused by the collisions of the particles with the sides of the container. If the gas is heated up, the particles will move faster and hit the sides of the container more often and harder. This causes the gas pressure to increase.